Okay, let's continue with where we left off in class. The limit comparison test that computes the limit of the terms of the sequence an and bn, and if we end up with a constant finite greater than 0, then either both converge or both diverge. So let's look at whether this series converges or diverges, and again I look at the an right here and I quickly do a divergence test, and I can see that the terms of that sequence go to 0, so the divergence test will be inconclusive. If I want to go and apply the limit comparison test, I have to come up with something to compare this to. So let's say I think of this as the 3 is like the loser term, and I'm going to compare it to bn equals, I guess, 1 over 2n. I'm going to use this because it kind of looks like that. And then we also know further that this series diverges because it's a multiple of the harmonic series. Now, unlike the direct comparison test, I don't have to worry about making this compare to this with a specific inequality, making sure that this is always bigger than this. I can just go ahead and apply this and see if it'll be useful for me, and I will get a limit that's a constant finite greater than 0. So let's go apply the limit comparison test. So an is this guy, and for my bn, I just pull this out to see if this will get me to where I want to get to. So now I'm going to look at the limit of an over bn as n goes to infinity, and again, this has the criteria that the terms be positive, and I do see that for both of these the terms are positive. So I go ahead and simplify this and see what ultimately happens. I have the limit as n goes to infinity of 2n over 2n plus 3, and we can see that this goes to, if I divide everybody by the highest power in the denominator, which is n, or apply L'Hopital, we can see that this just goes to 1. So this 1 is greater than 0 and it's finite, so I ended up with a value that I actually could use. And since the guy I came up with to compare it to diverges, this one also has to diverge because both of them have to behave the same way. So the limit comparison test says that both behave in the same manner. So since this guy diverges, so does the one that I was given by the limit comparison test. Okay, let's go look at another one. Does this series converge or diverge? So again, I have other options. I can quickly do a divergence test on this. That would be my first thing, and I can see that the limit of this guy goes to 0, so it looks like divergence test won't be useful to me. I can try to figure out if the integral test applies, but then I would have to integrate this thing, so I'm just going to go ahead and maybe resort to the comparison tests because all the terms of the sequence are positive. Now if I do a direct comparison, I have to play around with the inequalities. I'm just going to try to do the limit comparison test. So I have to come up with a bn to compare this an to. So let's try the bn by looking at who takes over, who wins in the numerator and who wins in the denominator. Now in the numerator it looks like the plus 2 is sort of the loser that I can kind of ignore. And in the denominator, if I expand this, I am going to have a polynomial of degree 3. So n cubed is the guy that takes over. Though I have an n squared, an n, and a constant involved, the guy that really takes over is going to be n cubed. So right now I'm thinking, let me just try this and see if this will work or not. So we're going to try to compare it to this sequence, and I have to analyze. I guess it starts at 3, so I'll start this guy at 3. What this corresponding series will do, and we know, actually it's an n squared, we know that this is a convergent p-series with p equals 2. So we already have information about our bn. Let's go pull out our an and do the limit analysis. So we got our an, we got our bn. Let's go look at the limits. Okay, limit of an over bn, and then I got to do some algebra. So multiply by the reciprocal, put them together, and this is pretty much where I'm at right now analyzing the limit. So once I multiply everything out, distribute the n squared, and multiply out n plus 3 3 times, binomial cubed, this is the expression I end up with, and we can see that the highest degree in the denominator is n cubed that I can divide everybody by, because that's the guy that takes over. Or if you have a rational expression, it's just the degrees are the same, so it's the leading coefficients, which means this is also going to be just 1 over 1, and it's a finite constant greater than 0. So LCT got me to a conclusion. I can decide that since the guy I compared it to converges, they both have to behave the same way, so the series given to me also converges. So my conclusion is that by the limit comparison test, the series given also converges. Okay, does this series converge or diverge? Now looking at the terms of the sequence, they look a little bit ugly, so if I had to do any integral test on this, it would actually be very ugly to deal with. Some of the things we can't integrate at all, so we can use the integral test. Also, if I have to do a direct comparison, it seems a little bit busy. There's a lot going on. So I will try to resort to the limit comparison test. Keep in mind, of course, you've done a divergence test already, and these guys actually go to 0, so that doesn't give you a conclusion. So let's go try to figure out a Bn to compare this guy to. So again, for Bn, in the numerator, it looks like 5 is the loser. The n can take over. And in the denominator, maybe this will behave like n to the 7th, but cube root of it, because n to the 7th takes over more than n squared. So I will ignore that and just say cube root of n to the 7th maybe will take over and see what happens. So that'll give me n over n to the 7/3 if I put it in exponential form. And then I have n to the 1 on top and n to the 7/3 in the bottom. So I'm actually going to be doing n to the 1 minus 7/3. And that'll give me n to the negative, I guess, 3/3 minus 7/3 is 4/3. So ultimately, I'm going to try to compare this to this guy, see if it'll be useful. So n took over on top, n to the 7/3 took over in the bottom, and then we simplified it to this. Now, what does that corresponding series behave like? Well, this looks like a p series, and since p 4/3 is bigger than 1, that guy's going to converge. So since p series with p equals 4/3 greater than 1, this guy is going to converge, and now we're going to go see how it compares to this guy. So we pull out our an and then the bn that we got that we're going to compare it to, and we're going to look at the limit of these two. Remember, it doesn't matter, as we said in class, whether you put the an on top or the bn on top. As long as the result is a finite constant greater than 0, you're okay. So I'm just going to do an over bn. So looking at the ratio of an to bn, looks a little ugly. We got to go do some algebra. So now we're here, and we have some expression that looks a little complicated, but we'll go ahead and distribute the n to the 4/3 and see what happens. So when I distribute that, remember this is n to the 1, and I add the exponents, I get n to the 7/3, and then 5n to the 4/3. And now, even though this looks really ugly, it looks like under the radical, the guy that takes over is n to the 7th in the denominator. But keep in mind, that's under the radical. So under the radical, n to the 7th takes over. If I want to find that dominant term to divide everybody by in the numerator, that's actually n to the 7/3 that's taking over. So it's very similar to the other ones we looked at. N to the 7/3 is the dominant term. Under the radical or the cube root, I will divide by n to the 7th, and outside by n to the 7/3. So under by, we're going to divide by n to the 7th, and outside by 7/3. To formally show what the limit goes to, this guy is already cubed inside, or inside the cube root, so everybody is going to get divided by n to the 7th. We're just doing a limit analysis. That's going to be limit as n goes to infinity. This guy just goes to 1. This guy goes to 5 over 4/3 on top, 7/3 in the bottom, so it looks like I have an additional n to the 1 in the bottom. 7/3 is 1 more than 4/3 over this guy turns into 1 plus this guy will be 1 over n to the 5th. And so now if I take the limit of that as n goes to infinity, this goes to 0, this goes to 0, and again nicely I get equals to 1, finite number greater than 0, so I will be able to make a conclusion. I just have to go back and see what I was comparing this guy to. So we end up with, I guess this converges as well because what we started with was a convergent p-series. So we'll say since we compared it to a p-series that converges, by LCT, the series given to us also converges. In class, we looked at this series and analyzed its convergence by doing a direct comparison test. Let's see if we apply the limit comparison test to this, what would happen. So in class, after some trial and error, we decided that if we compare it to k over k cubed, which is 1 over k squared, this corresponding series will converge, and this ended up being smaller than it, and that converged also. That was a direct comparison. Let's look at using the same guy for a limit comparison test. So this is our AK, this is the BK that we got that helped us earlier, and we're going to look at the ratio of the terms of the sequence. Simplify this a little bit, and we're going to get to having to analyze this limit, and when we analyze this limit, it looks like it's going to be big over big, so we're going to have to apply L'Hopital. So we apply L'Hopital's rule, derivative of the top, derivative of the bottom. Let's see what happens. And it looks like I end up with this expression, which still is going to be infinity over infinity. Let's try it one more time. So we're going to apply L'Hopital again, and notice we've had to apply product rules right here in order to do it. Okay, so now we end up with this when we simplify, and again notice I'm going to get big over big. So let's apply L'Hopital one last time. So one last time when we finally get to limit as k goes to infinity of 1 over 3k, which we know is 1 over big, which is 0. So we use the limit comparison test the way we had used it with this guy with a direct comparison in class notes. And after all this analysis, we ended up with our limit going to 0. Now, notice what limit comparison test said, that the limit I end up getting should be a finite number greater than 0. So with this case of the limit comparison test we're looking at, where we're restricting ourselves to just getting a finite number, and making a conclusion, it looks like I end up with something for which I can't make a conclusion using the limit comparison test. So it was actually better to use direct comparison for this. So again, no conclusion with the version of the limit comparison test we're looking at. And so as in class, we're going to just discuss a direct comparison quickly. Again, we're going to try this Bn that we figured out in class after some trial and error. And we know this is a convergent p-series. So ln of k, my ak, compared to the bk that we came up with. We said that the denominators are the same. Comparing the numerators, ln of k is going to be less than k on the interval we're looking at from 2 on. So this guy is always going to be below this linear guy. Y equals x, we said, looks like this. Y equals ln of k looks like that. So these guys will always be bigger than these guys. So we end up with an inequality that says the left side is less than this, all of this, which is 1 over k squared. And therefore we concluded that by comparison test, this guy is also going to converge, since the guy we compared it to converged, and this is actually less than that.